Welcome everybody to this new PCB-Investigator video tutorial. In this video tutorial, we're gonna show you how the DFT preparation tool inside PCB-Investigator works. So the DFT preparation tool helps you to plan test programs for your ICT or flying probe machine. And we have a design here with 12 layers and around about 1700 components. And yeah, it's quite complex, but there are already a lot of test points as component included in that case. So we're going to try first to make an ICT test program by using all the test points. So to start with creating a DFT program, we go to the analysis and open the DFT preparation, which is part of the production control edition of PCB-Investigator. And as you see here, this dialog opens and we are going to create a new test run. And we call it ICT planning. So there are different names already suggested, but you can enter an own name if you like. So now you see different tabs. The first tab is the test setup, then component setup, test model setup, net setup, probe setup, and the access overview. So most important thing is at the beginning in the test setup to decide what you want to do. You want to create a fixture program or a fixture-less program, so an ICT or a flying probe program. So we're going to start with a fixture program. Then you can decide where to place your probes. And as I saw, the test points are mainly or only on the top side. So we say we want to place only on top our probes. Then you can decide to exclude single pin nets or not, and to use the max test resources from net setup. So if you just switch to net setup, you see there are all the nets listed, and PCB-Investigator tries to recognize, dependent on the name, if it is a power, a signal, or a ground net. And depending on the net type, you see the pin count, and we suggest already a target test resources. That means how many test points or test probes or needles in our ICT adapter you want to have. So for power nets, PCB-Investigator suggests 2. For ground nets, he suggests 5. And for normal signal nets, 1. You can enter those, you can change those values. So just click on edit and you can say, in that case, I want 3 in this power net or 1 or whatever. So you're able to adapt this target test resources. And coming back to our setup, here the point is, do you want to use this test resources number or not? If you use a power net, which should have 2 probes, will have maximum 2 probes at the end. If you decide to not use it, as many probes as possible are created. So independent from your number which you want to have. Although this number is used to define if it is a forced probe or an alternate probe. So if you want to have 2 probes in a power net, and the layout says it's possible to have 5 probes in that net, 2 of them will become forced and the others will become alternate. So I decide to say I want as many probes as possible in this program, because maybe on the machine side I want to select which probe is really used or not. So and then we have different search tasks. As we only check for top, we only need the search task top, and it's possible to select how PCB-Investigator should find probes or find the perfect probe location and in which order. So now he tries to search first for test points, then for THTs, and then, if you like, also he can search for wires. And in that case, I say I just want to have TPs and THTs. Then we have available needles. So this list is already pre-filled with the 45, 50, 75, and 100 mil probes. And for each of them, you can define the real diameter, a name, and distances which this needle should have to high or small components. And every component which is larger than 3 millimeters is a high component, and each component which is smaller than 3 millimeters in height is a small component, and you have different rules for each needle. Then you have a standard minimum distance to components in general and a minimum distance between two probes. You always see here a description on the lower side of this dialog. So, and then we have the different settings for our three search tasks. So we have TP, VIA, and THT. VIA is what we decided not to use, but we can enter parameters for THT and for TP. So first of all is how should PCB-Investigator recognize that a component is a test point? And that mostly works by the reference designator. So you just enter possible reference designators. So it must start with P or with TP or with ICT or with MP. But you can enter also your own if you have special names for your designator. An alternative possibility is to use the pad recognition, which works on an ODB++ attribute on a copper pad. So even if you don't have components for test points, but you have copper pads, they can have the test point attribute in ODB++, and then PCB-Investigator knows that it is a test point pad. So then you can define a minimum pad size, so smaller pads will not be used for probes. And this is 800 micrometers in my case here. And yeah, then we come to the THT settings. So for THT settings, we have the possibility to say enable soldier mask analysis. That means that only pads are taken when there is an opening in the soldier mask. So that makes normally sense, because if there is a mask, is no mask opening, the soldier mask is going above the drill and is closing the drill or the THT. So if you have good data and if you have a mask layer, this should be enabled. Yeah, and then you can define minimum pad sizes or minimum annular rings to have a THT used as a probe. So then we come to the next tab. It's the component setup. And with the component setup, you see all your reference designators with some additional information like part number, package name on the side, the description, and so on. And you're also able to add own columns. So if you have certain properties on your design, you can add the property name and you will see these additional columns. So if you have special columns which are interesting for you, you can always add them in this view. But the main idea of here is to define different things. So I'd make just double click and I see the things I can't change because it's coming out of the layout. And then it's important, is it this SMT or is it a THT component? And normally with ODB++ data, all this information is already pre-filled and normally you don't have to change something here. But what may be important is if you need a 4-wire measurement for this, if it's a net link pin, so sometimes you have a 0 ohm resistor which links two pins, for example, two netzes, sorry, and then you can define if two netzes are shortened by this component. Yeah, then you can design, is it a component which is in the BOM? This is also a part which can be included in the ODB++ data, so there's the comp-ignore property, and depending on this comp-ignore property, this not in BOM is pre-filled. What is important to know is that at the end, if you export your program to a machine, also the components which are not in BOM, they are also exported. But they are exported with special values or with a special hint so that you can identify them later on. And the idea is to have the possibility to take a component into the program or leave it out on the machine side when maybe the variant changes. So it's part, but you will recognize it at the end in the test program. We'll show you this later. The other thing is omit in output. That means totally ignore it, as it is not existing. It's completely out. Yeah, then you have the possibility to define probe settings, which means you can define if a pin number should have a probe in every case independent from any rule. So you can say I want a probe here or I want no probe here in every case. So this makes maybe sense if you force connector pins, or certain connector pins. You say these 4 pins I don't want to have a probe, and the other 4 I need a probe in every case. So you can force them or say no probe, and then independent from the normal algorithm, this information is used in the background. And then we have test models. So regarding test models, this is the most important thing, let's say, because the test model itself defines the type of the component and how it is used, how it is checked at the end. We have a lot of different test model definitions here. So we have a resistor, capacitor, inductor, potentiometer, diode, LED, Zener, transistor, MOSFET, fuse, a jumper, switch, an optocoupler, and then we have special models for different machines. And you see there is already a value here. And regarding this, I just go back to the layout to show you. So what we already did with this design, we matched it already against our library, the EPL, the EasyLogix part library. Because as you see, it has a manufacturer part name, so it's in this tooltip, the C0805C something, and we also know the manufacturer's KMIT. And this one was already matched with our library, and the result is that we have already this MPN package. So this comes out of the EasyLogix part library, and it's showing the real package size. So not the CID package size, but the real package size of that special component from KMIT. And also properties are already there. So if you look at the properties, we also added a lot of properties from our EPL library to that component, and also to many of the others, as there are millions of parts in the EPL. And one important property which was also added by the EPL is this test model property. So this component has already the information about the test model, about the definition of this component. So it's a capacitor with 10% and a certain value. And this information is put in this XML file and is linked to that component. And this information comes out from the EPL in the matching process which we did at the beginning before starting with that video. So, and the point is that this test model information is already used and is already added to those components. That means a lot of components have already test models coming out of the EPL. Now you have the possibility for the other components where there's no test model. You can add test models on your own. But it's not making so much sense to do it in the component setup, because maybe you have the same part twice or 3 times and then you don't want to enter it 3 times. So that's why the test model setup tab is important, because here the components are summed up by their part number. And I can sort by test models, and I see the components or the parts which have no test models. The other ones here on the lower side have already all the test models from the EPL. But here we can just go to one of them and say, for example, these 3, double click, and then I have the possibility, if I know which part it is, this information I have to get somewhere, I can add, this is a resistor, and it's what was the name? I think it was 25 milliohm, 10%, and between the pins. So I add those information here in this test model setup. It was 26 ohms, sorry. So I change it to 26 ohms. So in that way you have to enter the test models. But what helps also is, if you already did this a few times, you are able to add those manually added information into a test model library. So it's possible to define a library, a local one or one in our cloud, and you can just say export the selected test model to the library. So we have to define a library first, and I take a LightDB file, and then I just say add it to this library. And I can say create only new entries or update also existing ones. And then this part is added in the library. And the next time when I got the next design, let's say, I can just again select this and say get this information from the library, and that helps me to. So this library is growing and growing and is learning. And with the next design, I don't have to enter all of them, but just a few of them. And the next time, even less, because it's reusable, this information. So we put test models into library and get it back from the library if we have a new layout. But the idea is to enter all the test models or get it from our EPL, or you manage it with an own test model library. Yeah, but this is what you do here. You enter the test models and decide if it is a component which is placed, which is in the BOM, or which is omitted. And yeah. Then next tab is the net setup, which we already have seen. So let's come to the probe setup. The probe setup means you have to define where a probe should be placed. This can be done manually by just say I want add a probe to mouse position, and the probe is there. You can also drag and drop it and put it somewhere. But of course, this is not the good idea. So what you do is I say automatic probe creation, and this automatic probe creation is using the things we define in our test setup. So search for TPs on THTs on the top side, depending on your needles, and define the probes. And here we are. So now we see that there are a lot of probes placed. We can go to the component and we can check. So it's a top test point. It's a TP reference. That is why the component was recognized as a component of the type test point. And PCB-Investigator places your probes with only one click, let's say. And you still have the possibility to zoom to each of them, and you can take a look into it. You see the definitions, the needle size which PCB-Investigator has taken, and it's a fixture, it's a type test point, and yeah, different other parameters. So you have force and alternate parameters, as I said. And you're still able to say, don't want this, like you can delete it, or you can add more manually, of course, or you can also move probes. But then you see here in the last column that it is not created by a rule. So as soon as you change something manually, you see it's not a rule created one. The idea, of course, is to make it by rules. And if you want, for example, that this J60 should be used as a probe on pin 26, let's say, then you just have to go to your component setup. It's already selected here. And then we say I want to have the pin 26 as a force probe. And when we go back to probe setup and say automatic probe creation, yes, we want to replace all of them, and then the 26 has a probe. And this is rule based. So not added manually, so if you click again and again, this probe will be created again and again. So the idea is to do as less as possible manually and as much as possible with the rules. Okay, so then let's take a look to the access overview. So here you have a summary. So you have a multi-pin nexus with one probe, with more than one probes, or with no probe, and single pin nexus. And you have a summary. You have this list of probes and nexus with probes. So nets with access 51. They are on top side, and so many probes they have, and a few of them are red because they have a probe, but not as many as the target test resources was. So we defined in net setup that the ground should have 5, but it has only 1. That's why it is red, but in the list with access. And here are the nets without access, and here are some test points which are not used. And if you take, for example, we look to the TP5, so it is somewhere here, too many layers on. Here it is the TP5 in the net. And if we just want to know why it is not used, we can go to the probe setup and take a look into this log. Because the rule must say that it is not used. So we search for TP5 and we see that the top test pad for this probe is too small with 406 micrometer. So let's take a look here to the TP5 and we see, but it is, if we go here, we see that it is totally in copper. No, it's not totally in copper, but it can be used as a probe. Let's just deactivate that one here. And I think the reason why it was not found is because there are two pads here on that side. And one is for the drill and one is larger, one is for the TP. And in every case, the larger one would be fine. So what we can do is we go back to there and go to the TP5, say show me the details and the TP5. So this is net VA ADC. And here the TP5 I want to add as a probe. So this one I added now manually, and the net becomes or moves from the lower list to the upper list. So now this net has a probe and everything is fine. So we can do this with other probes. We can also take a look here to the nets which are not having any probe. We can sort by the pin count and take a look, for example, to that nets. And we see there's a TP11.1. So somewhere here is a TP11.1 in this net here, and probably it's possible to have this TP11.1 also. We can change the log, look at the log, for example, again to see what happens, but probably it's also because of the wrong pad recognition. So that means we can go to show details and we just say we want to use this TP11. So, and then this net is in the upper list. And now we have 53 nets with access. So in that way, you can check the access overview. You can still manually add probes or improve the algorithms in that way. And at the end, you have a perfect planning for your whole DFT process on your machine. So you see the test points, and we are now able to say save. Oh, by the way, I saw the optimized needles. Yeah, that may be interesting too, because in the probe setup we have different needles, and the needle size. Let me take a look what needle size is here. So PCB-Investigator already uses different needles, and that is also interesting maybe to show you why. Because if there is something too close, so let's, for example, take this here, and we see there is a component very, very close, so that one maybe, or that one, then PCB-Investigator tries. If the 100 mil needles doesn't work, he can go down to a 40 or 50 or 74 mil needle and tries to take the largest one that is possible, but reduces step by step to find the one which works. So this is also an algorithm which is inside PCB-Investigator to adapt the needle sizes here. Okay, but now we are going to export. So save, and then we have the export. This is not on the screen. So now export. So we have different exports for Elowerk, for 3070 machines, for Seika, Speer, Takaya. So Takaya is a flying probe. Speer is also a flying probe here, but we can export Seika, 3070 or Elowerk. And each of that one, for let's try for example Seika, has then a different setting. And these settings depend on the machine which you export. So this is a typical machine settings for the Seika. You enter these once and it's reloaded every time, but you can also export and import your settings or reset to default. Yeah, and there are a lot of values which are important for that machine. They are all described in our manual, and probably people working with Seika know already this macro and device and this system which Seika, for example, uses. Takaya uses something different, so that export settings dialog is always adapted to have the parameters of the machine which you are using. Yeah, and then you say OK. and you select a drive where you want to have it, and then that's it. And the machine is exported. Yeah, so for creating an ICT planning, we can now just try the same for doing a flying probe. And as we already have done all the net setup and we have done all the test model setup, the easiest way now is to say I copy that one, and then I just rename it to call it flying probe planning. And then we change the setup here to be a fixture less planning, and we say only on top. Now we have a two-sided Takaya, let's say. So first on top, then on bottom. So this is the priority. And yeah, so these settings are the same. There's also short analysis done. And we search for TPs, THTs, vias, and also for SMTs. So we use the whole spectrum. And yeah, the minimum distances to the outline. This is the normal flying probe rule. And we have now TP, via, THT, and also SMT task, which is only existing for flying probe machines. And this depends where the probe is placed for components, for SMT components. So for example, you see if you want to test this component, it's not possible to test it in the middle of the pin because the component is there. So the flying probe needle or finger is not good if it is testing in the middle of the pad. So these rules define where it is tested, and this going from the outside to the inner side, and you can define these values, and the minimum value between the pin and the outer edge of the pad, and the percentage where in the middle it should be placed. So 50%, and a maximum offset, for example, a minimum offset. So you have different values here, which are all described. Yeah, but now just say probe setup, and we create new probes here. Yes. So here you see this probe is placed 50% between the outer edge of the pad and the MPN pin. So this is the real pin of this part of the real package, not the cut package. And this is the pin, and he's going in the middle with a probe. Yeah, so now he's placing all the probes for all the components here for the flying probe machine. And of course we have then a much better access overview. Only a few nets are not testable. Maybe there's a BGA or something. And yeah, in that case it works, of course, there's a higher access with flying probe, of course. And then again we can say save, and we go to, for example, Takaya. And we have a lot of settings for Takaya. In Takaya you need also some reference points. So this works. You can just take this and place it here, and place it here maybe, and place it here, and the other ones on the bottom side maybe. And then you have the typical settings for Takaya. You have a machine type, it's a single-sided or is it a double-sided, and all these values for diode measuring range, measuring times, these standard values which are used in the Takaya program. You have high-fly zones and so on, and all this information is filled. And the nice thing is PCB-Investigator in the background also does a check for serial or parallel components for resistors, capacitors, and inductors. So especially in Takaya, if there are two components in serial, two resistors in serial, and there's no probe in between, but a probe on each end of the sides, then these two components are done with one test, and PCB-Investigator calculates the serial resistance, and in the program there is the value of the serial resistance. And yeah, and you make a test, and all these serial and parallel things are already included in this Takaya export. And you will get a summary in a document, in an Excel document, where also you have the possibility to see at the end which components are recognized to be serial and parallel and what was the new test name, Interkaya. Yeah, so far so good. So of course, as always, if you have any questions regarding PCB-Investigator or our DFT preparation special, please just call us or write us an email to support@easylogics.de. We will be happy to help you. And yeah, we hope that you liked our video here. And yes, wish you a nice day and have a good time. Bye.